included the PTS system, the glycolysis and the pentose phosphates pathway system, and glycogen metabolic system. Okay, the controller, the key regulators of this system we identified should include the HPR phosphorylation status system and HPR subcellular localization system. The phosphorylate state of HPR binding with GLGP will control the different glycogen decomposition speed. Meanwhile, active PTS, the enzymes of PTS is in unphosphated state, so it's associated with glucose and glycogen. Also, the HPR subcellular location, when there has a phosphate group from enzyme 1 transferred to HPR, so the HPR will move from the pole location, the head location, to the whole cytosol scattered. And if HPR is in the pole location, it's mainly binding with the GLGP work for glycogen. If scattered in the whole cytosol, majorly for uptake of glucose. Okay, and also including the gene expression controlling by the enzyme 2A and the CMP-CRP system, and also FDB-CRE system. I will describe this later. Okay, our regulation system can be divided in hierarchical maps, including the metabolism level, flux levels, protein levels, and the localization levels and the gene expression levels. Yes, and you see the blue one. The blue one is from PEP to enzyme 1 dimerization. This means the enzyme 1, the dimer speed of enzyme 1 is the bottleneck of the PTS system run. So this is the starting point of the phosphate group flux. Okay, comes here and controls two pathways. One is localization control. HPR is used for glycogen or for glucose. And also the phosphate status of HPR controls the speed of decomposition glycogen and also the glucose uptake speed. Okay, if detailed things, you can look at my paper. Since now, okay, the mechanism of metabolism part we have studied, and also regulator, we also know it. But the controlling method, we should, how we can start it, this one. Okay, we have to use the computational models to simulate. Then we can know how dynamically this regulation systems controls this device. Okay, so we have to construct our computational model. For the glycolysis models, the central metabolism pathways, the classic OD models is from Chachanov, but 2002 years. This is quite classic, based on 8. Okay, and existing PTS study, their models have been studied quite well by Rodriguez and Rowers. Yeah, their models is quite good and details based on the mass balance theoretical models. This name they called. Okay, but for the glycogen metabolism pathway, currently do not have specific to the special for glycogen, this metabolism pathway. I didn't find any computational models detailed describe this part. Okay, so we try to construct these models. In device part, we include the OD models from glycolysis, glycogen of metabolic pathway. This part I use the top to down method to according to the concentration of both sides of metabolic concentration and to estimate the parameters. Okay, and the mass balance theoretical PTS modeling, and I will select all the regulation systems. Okay, the model 1 we set up in the Petronite. Okay, we transplant Chachanov's model of central metabolism into a Petronite model. Okay, successful. The result is similar. we got the same result as Shashagnose. The second model we set up is transplanting the Rowe and Rodriguez model of PTS. Okay, result also showed similarity. Okay, then we integrate these two models to a combined one. The model 3 include the glycolysis and the PTS system. Then we add our selected HPR and enzyme 2A centered regulation system together with this model. We construct model 4. This is our final model, including that one, glycolysis and glycogen metabolism pathway and the PTS system, and also the HPR subcellular location control box and dimerized enzyme 1 dimerized PTS speed control box and another control box and gene expression control box. So run these models in Cell Illustrator, we got the result. And in this result, the red bar is the biological data, and the simulation result is the line. So the major metabolic concentration is a condensed. Only some didn't, not not all the metabolic concentration we calculate the same to the biological one, but the major one is okay. And also include in that line, that row is the PTS proteins behavior. And the end one, this line, the bottom line, is the regulator levels. Okay, how to analyze this result? We divided the whole cells, the E. coli life into six phases. Okay. In the first phases, you can see here, glucose and glycogen both have in E. coli. So this means that HPR is located in the head. So a little bit glucose active the PTS to be N-phosphate. So in the second part, the N-phosphate PTS of the pole located will catalyze glycogen in a very high speed. So this is the major position for glycogen is used. Okay, then glucose, not so quick glucose uptake has been activated because now the HPR has been activated, driven by the enzyme 1 to scatter from the pole area to the whole cytosol, work for glucose. So, but it's not so highly. So the glucose is uptake, but in a low speed in the later lag phase. Okay, come to the log phase, first part of log phase. Okay, this majorly glucose is uptake in this phase. We can see, yes, the sugar group flux speed is quite quick from glucose in this phase. Then from later log phase, different is now the extracellular glucose is less and less. So PTS, that step by step to become phosphate. That means inactive. Okay, in the stationary phase, okay, no more glucose outside anymore. So you see all the HPR has shrinked into the head part. So in this period, the phosphate HPR catalyzes a low-speed glycogen for the E. coli to survive for a long time. If too quick, the E. coli will use up all the energies to die. Okay, logically say this is a composition of glycogen. We can see if from FTP to CRA system, we call this parameter alpha, and from phosphate enzyme 2A to CAMP-CRP system to control the GLGCA expression, we call the beta. Okay, this system's activation is like that. Okay, in mathematics, logical expression, I calculate it's alpha plus beta equals to gamma. Okay, this is a decomposition of the glycogen. Okay, the subcellular location of HPR is in the pore is lambda. Okay, if the HPR is in phosphate state, it's a rho, but in HPR in unphosphate state, nothing. Okay, and these both parameters controls data of decomposition of glycogen. Okay, this is a quite complex logical like that. Okay, now we can see in the lag phase. Okay, if alpha is off and beta from on to off, it means off. This means the glycogen composition is null. Okay, and under you can see from this side, if the HPR is located in the pore, and it's stayed from phosphate to unphosphate. This means if the HPR located in the pores and in unphosphate state, okay, glycogen will decompose in the fastest phase. This majorly the utilization of glycogen is in this period. Also, all the following phases is accordingly. Okay, based on the former studies, I constructed these models. I think it's quite like this system, quite like a hybrid power car now. The glucose uptake is like engines, and the glycogen is worked like batteries. Okay, we have a sugar source switch to control which sugar source has to be used, and also gear system to control the utilization glucose speed. Okay, also we have the systems feedback circuit to control the sugar storage system. That is like the charge system of recharge system of the batteries. How this system worked? Ah, yes. For a car, we need the ignition system. In this system, the lock is I think, it is the enzyme 2CB, the membrane enzymes, who is the first enzymes from the membrane side to uptake glucose. When there is glucose in the mediums, okay, the lock is turned on. Okay. When this car is parking, okay, parking means we only use the battery to maintain this, maybe the computer system of the car or some other security systems. Okay. When this hybrid car is running at low speed, okay, the ignition system is turned on, and we use glycogen, we use the battery to run this car. And if the car runs in the freeways, running at high speed, okay, we use the glucose uptakes. These engines to support much more powers. This is my thinking about this. Okay, achievement of our work of this step is HPR and enzyme 2A glucose are the key regulators of the glycogen metabolism in E. coli. All of our study until now, maybe we can draw a conclusion. Glycogen is quite important. When we studied central metabolism pathway, we should take the glycogen metabolism into account, I think. Is it too fast? Okay, this is our future work. We want to expand this glucose metabolic pathway to other carbohydrates like lactose, or use the CCR system, induce exclusion system, and then at last maybe the whole metabolism. But I know it's far away, I think. Oh, so much for this. Thank you very much.
Any questions? Anyone?